In the last session, we have discussed about Mendeleev periodic table, and in this session, we'll be discussing about modern periodic table. So, the modern periodic table, if you look at the modern periodic table, it consists of 18 vertical columns called as groups and 7 horizontal rows called as periods. And the structure of the modern periodic table looks like this. Hydrogen, lithium, sodium, potassium, rubidium, cesium, francium, beryllium, magnesium, calcium, strontium, barium, radium, and scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, cadmium. And then here you have lanthanum, hafnium, tantalum, wolfram meaning tungsten, rhenium, osmium, iridium, platinum, gold, mercury. Then you have your lanthanum, sorry, not lanthanum, you have here actinium, rutherfordium, and so on. And then here you have boron, aluminium, gallium, indium, thallium, carbon, silicon, germanium, tin, lead, nitrogen, phosphorus, arsenic, antimony, bismuth, oxygen, sulfur, selenium, tellurium, polonium, fluorine, chlorine, bromine, iodine, astatine, and helium, neon, argon, krypton, xenon, xenon. This is the basic structure of the modern periodic table, and it's divided like this. Like this, and like this. So I didn't finish the 7th period because still there are some elements just recently discovered, and this is the modern periodic table. What are the features of modern periodic table? The first point is the modern periodic table is divided into 18 vertical columns, 18 vertical columns which are called as groups, and 7 horizontal rows called as periods. 7 horizontal rows called as periods. So if you take this 1, 2, and here 10, and here 6, 1, 10, and 6, totally 18 vertical columns. And these groups are numbered in old system as 1A, 2A, like that. This is the 1A group, the 2A, and this is the 3A, 4A, 5A, 6A, and this is the 7A, and this is the 8A. Okay, and these are the horizontal rows called periods. The first period, second period, third period, fourth period, fifth period, sixth period, and seventh period. These groups in old system, they are numbered in Roman numerals. Roman numerals as 1A, 2A, 3A, like that. And the horizontal periods are numbered as in Arabic numerals. Actually, this one, and here you have this 1B, 2B, and here you have 3B, 4B, 5B, 6B, 7B, and these three groups together is called as the 8B group. Now, this 1A, 2A, 3A, they are in the old system, the traditional system, the classical system. But in IUPAC system, even they are numbered in Roman numerals simply from 1 to 18, like as first 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and this is the 18th group. 18th group. So, what does this group number and what does this period number indicate? The group number indicates number of valence electrons. Number of valence electrons. Like the first A group elements have 1 valence electron, second A group elements have 2 valence electrons, 3A group elements have 3 valence electrons, and 8th group element have 8 valence electrons. And what does the period number indicate? The period number indicates number of orbits or number of shells. It indicates number of orbits or shells. The first period elements, hydrogen and helium, they have only 1 orbit or K shell. The second period elements, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, they have 2 orbits, 2 shells, K shell, L shell. Third period elements have 3 orbits or 3 shells, K, L, M shell. Fourth period elements have 4 orbits or 4 shells, K, L, M, N shell also, like that. Now, how many elements are there in each period? The first period elements has 2 elements, hydrogen and helium. There are 2 elements in the first period. Whereas in the second and third period, there are 8 elements, 2 here and 6 over there. 1, 2, and 3, 4, 5, 6, 7, 8. 8. Even in the third period also there are 8 elements. So there are 8 elements each in that each period. Next, about 4th period and 5th period, and also 1, 2, 3, and 4th, 5th have how many elements? The 4th and 5th period elements have these 2 elements, here this 10 elements, and then here 6. So 2 plus 10 plus 6, and 5th period also 2 plus 10 plus 6, 18 elements you have here. 18 elements here. And then in 6th and 7th period, we have, along with these 18 elements, you have 14 more elements placed separately below the main body. So here 18 and down 14, here also 18 and down 14, total 32 elements. So 32 elements each. Okay, now there are actually 14 more elements. See, for example, lanthanum. Lanthanum is 56 atomic number. And then after lanthanum, you have these elements here, separate. Cerium. So after lanthanum 56, you have here cerium, whose atomic number is 57. And then from cerium to lutetium, whose atomic number is 71, and then you have 72 half name here. So from cerium 57 to lutetium 71 elements, the 14 elements, they actually come under third 3B group and 6th period. Similarly, after actinium also you have 14 elements placed separately. Here actinium atomic number is 9. The thorium 90 starts here till lawrencium 103, and after 103 Rutherfordium 104 is placed here. So these 14 elements here and the 14 elements down, they are placed actually below the main body of the periodic table. As I said, after cerium 56, after lanthanum 56, the element cerium 57 starts here till the 14th element lutetium 71 and again 72. See why? Because we can't break this periodic table and put these 14 elements here in this space. In this space we can't accommodate those 14 elements, because the shape gets out and becomes disfigured, the periodic table. It looks very crooked. So we can't fit these 14 elements here, which are called lanthanides. And we can't place these 14 elements here. These are called as actinides. 14 elements here and 14 elements here can't be accommodated because it gets disfigured. So better we separate this 14 lanthanides and 14 actinides, separate from the main body of the periodic table and placed below it. Okay, now also the periodic table is divided into 4 blocks. The S block, P block, D block and F block. Here the 1A and 2A groups, these two are included under the S block, whereas from 3A to 7A, all these they are included under the P block, whereas from 3B to this 2B, all this middle block is called as the D block, whereas the lanthanides and actinides together make the F block. Together they make the F block. So remember, S block includes the leftmost groups 1A and 2A. It includes only metals, whereas the rightmost block, P block, it includes metals, non-metals, metalloids, all. See, for example, what are the metalloids here? Boron is a metalloid, silicon, germanium, arsenic, antimony, tellurium, polonium. These elements are metalloids. Metalloids meaning these metalloids have properties both of metals and non-metals. Like metals, these metalloids are electropositive. Like non-metals, these metalloids are brittle. So they share the properties of both metals and non-metals. So somewhere the intermediate they are placed, these metalloids. And left to these all metalloids are metals, and right to these metalloids are non-metals. So if you look this metalloid's position, it looks somewhat like a staircase, like this. Right of this staircase you have all non-metals, left of this staircase you have all metals, and on this staircase you have metalloids. It includes, so P block includes all non-metals, metalloids, metals, metalloids and non-metals, all are placed here. So based on what criteria these S block, P block, D block and F block are distinguished? S block elements have their valence electron in S orbital. P block elements have their last valence electron in P orbital. D block elements have their last valence electron in D orbital, and F block elements have their last valence electron in F orbital. And these D block elements are also called as transition metals. They are also called as transition metals. And the F block elements are also called as inner transition metals. They are also called as inner transition metals. Why transition metals? Because we find left side all metals and then metalloids and then non-metals. So slowly the metallic character is undergoing change or transition into non-metallic character. Transition means change. Slowly the metallic character is undergoing a transition through these D block elements into non-metallic character. That's why this is called as a transition block or transition metals or D block. And inner to this transition metals we have some more 14 and 14, total 28 elements. They are called as the inner transition metals, like that. Now this is the structure of the modern periodic table, and as we move from one period to the next period, number of orbits increases. I said because the period number indicates number of orbits. So first period elements have only one orbit, two orbits. This the third period elements have three orbits, fourth period elements have four orbits, fifth period elements have five orbits, sixth period elements have six orbits, seventh period elements have seven orbits. So the number of orbits increases, so the atomic size also increases. We'll come to the atomic size later. But this is the structure of the modern periodic table, and all these 7A group elements, they are called as noble gases. They are called as noble gases, or they are also called as inert gases, or also called as zero group elements. Why zero group? Because their valence is 0. 8 minus group number 8 minus 8 is 0. Inert gases, or it's also called as aerogens. Aerogens. Whereas the 7A group elements are also called as halogens. Halogens. Halo meaning salt, and gen forming salt forming compounds like the common salt NaCl, calcium fluoride, magnesium chloride. The common salts all are compounds of these 7A group elements. So they are called salt forming elements or halogens. And the sixth group elements, they are called as chalcogens. Chalco meaning ore. Ore. They form ores, like the typical iron ore is hematite, Fe2O3. So it's an oxygen compound. Or the typical aluminium ore is bauxite, Al2O3. That's also an oxide. The typical copper ore is copper pyrite. That's a sulfide, Fes. The mercuric ore, cinnabar, HGS, and iron pyrite, Fes2. All these are of 6A group elements. So the typical ores what we found in the Earth's crust, all are compounds of the 6A group elements. So that's why called as ore forming elements or chalcogens. And this fifth group elements, they are called as nicogens. Nicogens. Nico meaning poisonous, because most of these 5th group elements, they form poisonous compounds. You take NH3, ammonia, it's a very poisonous gas. PH3, phosphine, it's a poisonous. So all these 5th group elements, they form very poisonous compounds. Mostly they form poisonous compounds. That's why they are also called as nicogens. So this is the basic architecture of the modern periodic table. And now we will discuss some periodic trends. Periodic trends. First, I would like to discuss about the atomic size or atomic radius. R. See, remember, all other periodic properties, whether ionization energy, electron affinity, electronegativity, electropositivity, metallic character, non-metallic character, all other periodic properties are directly or indirectly related to atomic radius. So atomic radius is very important because the size of the atom, the radius of the atom determines all its properties. Its oxidizing power, reducing power, metallic power, non-metallic character, all the properties are determined by the radius of an atom, size of an atom. What's actually an atomic radius? See, for this, let us take a sodium atom example. Some atom, like sodium atom. Sodium atomic number 11. So it has 11 electrons as 2, 8, 1. Now, this sodium atom, if you look at the atom, this is the nucleus. This is the first orbit with 2 electrons. And this is the second orbit with 8 electrons. And this is the third orbit with 1 electron. So what is the size of this atom, sodium atom? The radius of an atom is the distance from the center of the nucleus here till the valence orbit. That's called radius. So radius of an atom is the distance from center of the nucleus to the valence orbit, the last orbit. That's the radius of an atom. But remember, we can't determine the radius of one single isolated atom because atoms are so small, and we can't detect exact location of the electron in the valence orbit, because if an electron is at this place, we know that its position, but electron is not stationary, it moves, so we can't see where is the electron. It's like an electron cloud, so we can't locate the exact location of the valence electron. So we can't find the valence orbit, and so we can't find the radius. But we can find the distance between two nucleus. So once again I'm telling you definition of atomic radius. It is the distance from the center of the nucleus to the valence orbit. But as I said, we can't find the radius of one atom. What we will do is we will consider two atoms joined together. Like for example, let's take another sodium atom. This is its third orbit with one valence electron, the second orbit with 8 valence electrons, and the third orbit with 2 valence electrons, and this is a nucleus. So here also this becomes the radius. Now we can find the distance between these two nucleus. We can find the distance between the two nucleus. If this is the distance between the two nucleus, that's called as the internuclear distance. That can be found, distance between two nucleus, by for some alpha ray scatterings and some calculations we can measure the distance between two nucleus. That's called internuclear distance. And then we will do half of that internuclear distance, then we will get the radius. So radius of an atom is just half of the internuclear distance. In that way we can determine the atomic radius. Just take the distance between the two nucleus of that atom and then do half of that internuclear distance. So numerically atomic radius is simply half the internuclear distance. Okay, now this atomic radius is of different types, but important is the metallic radius, and the other is covalent radius. It's simple. Metallic radius is the half the internuclear distance between two atoms bound by a metallic bond. Sodium is a metal, so these two sodium atoms are bound by a metallic bond, and half of that internuclear distance is the metallic radius. So what is a metallic bond? See, when two metal atoms are close together, there is a force of attraction between the nucleus of one atom and the valence orbit of the neighboring adjacent atom. Attraction force, that's a metallic bond. Here the nucleus of this metal atom with the valence electron of this metal atom, there is some attraction. That's a metallic bond. So when these two metal atoms are bound together because of that metallic bond, you can know the internuclear distance, and half of that is a metallic radius. Just it is the half the internuclear distance between two atoms bound by a metallic bond. Similarly, you consider two non-metals or two atoms bound by a covalent bond. For example, take chlorine 17 and another chlorine 17 atom. So this is the third orbit with 7 valence electrons, second orbit with 2 valence electron, and first orbit with 2 valence electrons. Sorry, here 8 and 2. So the nucleus. Here also we have third orbit with 7 valence electrons, second orbit with 8 valence electrons, and first orbit with 2 valence electrons. So it's the nucleus. Here these two chlorine atoms are bound by a covalent bond because they have 7 valence electrons. They share that one electron to form a covalent bond. Here also we get the internuclear distance, and we'll do half of that. We get the covalent radius. So covalent radius is half the internuclear distance between two atoms bound by a covalent bond. And this atomic radius is measured in picometer. It's measured in picometer, and 1 picometer is 10 to the power of minus 12 meters. 1 picometer is 10 to the power of minus 12 meter. But how does it vary in a group and period? How does it vary in a group, and how does it vary in a period? See, I said to you, as we move down the group, we are actually passing from one period to next period. So as we move down the group from one period to other period, number of orbits increase. So definitely the size increases. If you look at hydrogen, this is the first orbit. Then look at lithium, second period, so it has 2 orbits. Next, sodium, it belongs to third period, so it has 3 orbits. Next, potassium, it belongs to fourth period, so it has 4 orbits, 1, 2, 3, 4. And then look at rubidium, it belongs to fifth period, so 5 orbits, 1, 2, 3, 4 and 5. Then it has 5 orbits. So as you see, the number of orbits are increasing down the group, so definitely the size increases. But what about in a period? For example, let's take the second period. See, second period you have beryllium. Here you have beryllium, and it also has 2 orbits. First orbit, second orbit. Then you have boron. Boron is also second period, so it also has 2 orbits, 1, 2. Next, carbon. It also is the second period, it also has 2 orbits, like nitrogen, oxygen, fluorine. See, you should observe here that as we move left to right in a period, the atomic size is decreasing. You should be getting a doubt. In a group, as number of orbits are increasing, the size increases. But in a period, the number of orbits is the same, so the size should remain same. But no, it decreases actually. Why? For example, look at the second period. All have 2 orbits. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, all have 2 orbits. So 2 orbits, the size should be the same. But the second orbit slowly comes close to the nucleus. It shrinks in size as we move from left to right. Why? Why? Because as we move from left to right, the nuclear charge increases, because atomic number increases. So look at here. For example, what is the atomic number of lithium? 3, boron 4, beryllium 4, boron 5, carbon 6, 7, 8, 9 and neon 10. So as we move from left to right, the atomic number is increasing. As the atomic number increases, the nuclear charge increases. As the nuclear charge increases, the nuclear force of attraction, the nuclear pull on the valence orbit increases. So the valence orbit is pulled more strongly, closer and closer to the nucleus. So the second orbit comes close to the nucleus and it shrinks in size, so the atomic radius decreases. For example, look at lithium. Lithium has 3 protons, so 3 plus charge and 2 orbits. Boron has 4 protons, so 4 plus charge, so this 4 plus charge has a greater nuclear charge, so it has a greater force of attraction on the valence orbit, here on the second orbit. So second orbit comes close to the nucleus. Next, boron 5. Boron 5, atomic number is 5, so it has 5 protons, so the nucleus charge is 5 plus, and so more charge. So the first orbit and the second orbit is pulled more strongly. So as you move from left to right, the number of protons increases, so the nuclear charge increases, so the nuclear pull or the nuclear force of attraction on the second orbit or the valence orbit increases, so the atom slowly shrinks in size. You may be getting a doubt, as protons increases, even the number of electrons increase, because atomic number is not only the number of protons, it's also the number of electrons. But these electrons are in the same orbits. Whether you take lithium 3 electrons in the 2 orbits only, beryllium atomic number 4 electrons, but 4 electrons is 2 orbits only. This boron atomic number 5, so 5 electrons, but 5 electrons again in 2 orbits only. Imagine there are 3 people in a circle, 4 people in a circle, 5 people in a circle, 6 people in a circle. How many ever number of people are there? But there is one circle only. Here also, how many ever electrons are there? They are within restricted to 2 circles only. So the size should remain same, but no, because as the protons are increasing, the second circle is pulled closer and closer and strongly towards the nucleus, so the size gradually decreases. So as we move from left to right, as atomic number increases, number of protons increase, and as protons increases, nuclear charge increases. As nuclear charge increases, the nuclear pull on the valence orbit increases, so the valence orbit is brought closer and closer to the nucleus, so the atomic size decreases. Because atomic radius is so important, it should be very clear. Now coming to the second periodic property, ionization energy. Ionization energy. Ionization energy is also called as ionization potential, IP. What is this ionization energy? Ionization energy is the amount of energy required to ionize an atom or to remove an electron from an atom and make it an ion. But to calculate ionization of an atom, the atom should be in a separated form, in an isolated form. It should be a neutral form, it should not be some Na plus or Na minus. It should be Na, and it should be in gaseous state. So to calculate this ionization energy, the atom should be in a neutral state, in an isolated state, and it should be in a gaseous state. From such an atom, let us think we have this sodium atom. Sodium atom is here with 1, 2, 3. So this first orbit 2 electrons, second orbit 8 electrons, third orbit with 1 electron. So this is sodium atom whose configuration is 2, 8, 1. Okay, this is the nucleus. Now this sodium atom, it should not be in solid state, remember, because some elements are in solid state, some elements are in liquid state, some elements are in gaseous state, and solids have a greater interatomic forces, liquids have weaker interatomic force, and gases have still weaker interatomic force. So we should not consider these atomic forces into consideration, interatomic forces. We should, when we calculate ionization energy, we should consider an atom completely in gaseous state. I mean, that should be a generalized definition. To generalize the definition of ionization energy, we have to consider atom in gaseous state. So you take a sodium metal, convert that sodium metal into gaseous state, and from that gaseous state pick up a sodium atom which is free from all other sodium atoms, isolated state, and from that sodium atom it should be neutral state, again not in Na plus or Na minus, neutral state, neutral sodium atom. From such a sodium atom, how much energy you give to remove the last electron, last one valence electron, that is called ionization energy. Okay, so when I supply energy to this atom, the atom loses electron. The atom loses electron and the third orbit becomes vacant. And here your second orbit and first orbit. First orbit 2 electrons and 8 electrons. Now this is not Na, it's Na plus, whose configuration is 2, 8. Okay, it's a nucleus. So here, how much energy you give energy to the atom, it gives you electron, and that's energy given is called as ionization energy. But you give electron, it will give you energy, and that's called electron affinity. We'll discuss later. So ionization energy is the energy given to an atom to lose electron. So now I'm telling the definition of ionization energy. Ionization energy is the amount of energy. Ionization energy is the amount of energy required by a neutral isolated gaseous atom to lose the last valence electron. So what is ionization energy? Ionization energy is once again the amount of energy required to remove the last one valence electron from an isolated neutral gaseous atom. Okay, to convert this neutral atom into a unipositive ion, unipositive means +1 charge at ion, the energy given is called as first ionization energy. First ionization energy. And is this first ionization energy more or less than the second ionization energy? For example, Na plus, lose electron or gain electrons now? It's very stable. It will not lose any more electron. For example, let's consider there is one ice cream. That ice cream cost is 8 rupees. And you are badly in need of that ice cream. You will be happy only if you have that ice cream today. So, but you are having 9 rupees. So if you are going to purchase that ice cream, if anyone asks you that 1 rupee, you will easily give, because you are having 9 rupees, that ice cream is only 8 rupees. So you can donate 1 rupee to him with not much, you will give him that 1 rupee. Now you are going. Now one more person comes and asks you 1 rupee. Will you give 1 more rupee to him? No. You have 8 rupees and that ice cream cost is 8 rupees. So you will not try to lose any more money. So, but there is a possibility you try to